So my name is Craig Kaplan. I'm the CEO of IQ Company, which is a consulting company. It's been around since 1993, focused on artificial intelligence. In this talk, I am going to argue that the first AGI has to be the safest AGI. I am going to suggest that the fastest and safest approach to building AGI is one that involves the collective intelligence of agents. And to do this, I'm going to draw inspiration, as we saw in some of the prior talks, from some of the brilliant scientists that have gone before. I'm not going to go all the way back to Aristotle, although I thought that was fascinating in Yoshua's talk. We're going to go back to some of the scientists that were there in 1956 when the field of AI was named at that Dartmouth conference: Minsky, Shannon, Newell, and Simon. And it's a short talk, so we'll just have one slide on each of those guys, hit on one of those key ideas, and then see if we can bring it all together in terms of how that might inform building a collective intelligence approach to AGI. Okay, so we'll start with one slide on motivation. So probably a lot of you have seen this statement from the Center for AI Safety on the left there. Mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks such as pandemics and nuclear war. What impressed me was the range of signatories. I mean, you had everybody from Bill Gates, Sam Altman, Paul Rosenblum, who spoke earlier at this conference. Many distinguished scientists as well as business leaders are all saying, look, we need to pay attention to this, so it's very high stakes. Yet there hasn't been enough work, in my view, to sort of get ahead of the curve. And that's really why I got back into this. I was in industry for many years and designing intelligent systems. And I came back to AI because I felt like there was a very short time window. So we all know Moore's law, that computational power doubles approximately every 2 years. Some are saying Moore's law is dead now. But we have another law, right, from Jensen Huang at NVIDIA. Wang's law, every 1.03 years, GPU power is doubling, not just because of the chip design, but because of the software innovations that are going along with that. On the right, you can see a slide, a shout out to Ray Kurzweil, who unfortunately is not here. Obviously wrote The Singularity is Near, and a couple months ago came out with the next book, The Singularity is Nearer. And here's a slide from Ray that basically shows on a log scale that price performance of computation has been going up in pretty much a straight line since 1939. So if you extrapolate, we're going to have large language models that are 1,000 times more powerful than GPT-4 within a decade. And one question is whether we're going to be in a winner-take-all scenario. Now, those scenarios are very rare in reality. A lot of times in Silicon Valley, especially, people talk about winner-take-all, first-mover advantage, you dominate all the other players. AGI may be one of those cases where if you have an AGI or a superintelligence system that self-improves, and if the rate of self-improvement is very fast, that sort of later systems just never have a chance to catch up, and that system ends up dominating. So it's not guaranteed, but if that was the case, it certainly would be very important that whatever system is developed first is also the safest system. Okay, so that's the motivation. So my main thesis in this talk is going to be that collective intelligence, which is an area I've spent pretty much my entire adult career working in and designing systems, is the fastest path to AGI. So what is collective intelligence? Probably most simply, you can think of it as the idea that two heads are better than one, and you can extrapolate that to millions of brains working together can do really phenomenal things. So I've lived this and built systems that have harnessed collective intelligence of millions of retail investors, for example, to get an edge in Wall Street and sort of beat the very best hedge funds. So I know from practical experience that this works. The question is, can we apply this thinking and this kind of design to AGI? And currently, you can think very simplistically that there's kind of two major camps. There's the camp that says, let's build an Uber LLM, GPT-5, GPT-6, GPT-7, just keep taking the parameters up to from hundreds of billions to trillions of parameters, buy more and more GPUs, more and more data, and somehow AGI or superintelligence will emerge. We've heard at this talk at this conference a number of talks from folks saying, wait a minute, it seems like there's some sequential problem solving and planning that may be missing. Maybe there's some limits to that approach. Not clear that that's going to work, but there are definitely people who are trying to do that right now. There's another approach that I'm going to advocate, which is take the models that you have right now. They don't have to be super intelligent. They don't have to have AGI. Take the existing models, find a way to integrate them, and the collective intelligence of many AI agents and human agents together will give you AGI level performance and maybe even super intelligent performance. And so when we talk about agents in this scheme that I'm going to describe a little bit more detail about, we're talking about both AI and human agents. And from a safety point of view, it's very important that human agents are involved, as we'll see. Okay, but let's first get a little inspiration from some of these great minds that have come before. So Marvin Minsky from MIT wrote a book, 1988, Society of Mind, which basically said, or laid out the hypothesis that you could get true intelligence, he called it true intelligence, from the operation of many much simpler intelligences. Much simpler cognitive systems could come together, and by working together, and he was a little bit nebulous about how you would integrate them, but the idea was they could combine and form this true intelligence. And it's kind of analogous to how human minds work. So my background as a cognitive psychologist, we did a lot of research on this. Human brains, human minds have different modules. Not all of them are super intelligent. You have visual system, different kinds of perceptual systems, but they all work together, and you end up with human level intelligence. And so modularity has a lot of advantages, and just at that very high level, this is kind of the idea coming from Minsky that maybe collective intelligence would be an approach to try rather than training the Uber LLM. Okay? Second idea, Claude Shannon, another one of the folks that was there when the field of AI was named, known for information theory. So I'm just going to take one very simple, piece of inspiration from Shannon, the notion of information being proportional to the rarity of an event. So if you think about training large language models, for example, we're basically taking the entire internet or multiple Library of Congress's worth of information and shoveling all that data at some machine learning algorithms, and out comes GPT-4, which sort of behaves at a mediocre level in a lot of ways. And one of the reasons that it doesn't sort of act more intelligent than it does is that there's a lot of kind of mediocre information out there on the internet. And it may be that you need higher quality data. And so where do you find that rare, high quality data? I would argue that a lot of it is locked in human brains. It's not necessarily out on the internet. It's in the brains of all the people in this room. Some of people's ideas are definitely in papers, but a lot of it is knowledge that really is not accessible for training. And so if there was a way, for example, to get all the brains in this room working together on a network as human agents with AI agents, maybe there would be a way to expose that network to this higher quality information, and maybe that would be helpful in terms of getting a higher level of intelligent performance out of the system. So that's the idea we're going to take from Shannon, that good information is somewhat rare, and maybe we need to find it in human brains. Okay, then we're going to take a third idea. So when we looked at Minsky, he said, well, let's have lots of agents working together somehow. Newell and Simon, 1972, wrote a book called Human Problem Solving. Some of you are familiar with it. It's just about as thick as Ray Kurzweil's book on the singularity. Both of them can be used as paperweights. They're pretty dense books. But what was great about that theory was that it proposed a rigorous, unambiguous problem-solving framework that basically described problem solving, whether it's done by a human or by an AI program, as happening in a problem space. You move from state to state, you apply operators. At every step, you knew exactly where you were, and you could create a record of the problem-solving solution. So that record can be unambiguous, auditable, transparent, right? So a big problem with LLMs and with the Uber LLM approach to developing AGI or superintelligence is that these things are black boxes, right? I mean, it's absolutely crazy. We know how the algorithms work, but we don't know how they store their knowledge, really. We don't know where the representations are. We can't predict what they're going to do. We try to do whack-a-mole RLHF to beat them into submission so they don't do things that are too egregious. And then we're going to just try to make a bigger one. I mean, it just seems a little bit crazy. Maybe a better way would be to design a system for AGI where there's some transparency. We can actually see where the agents work. In a human society, we don't have to look in each of our brains. It's a black box. My brain's a black box, your brain's a black box. I don't need to know what's inside your brain. We have, at the societal level, laws and ways of social norms that regulate our behavior. And so we don't run in fear that somebody's going to do something crazy because we can see the behavior and how all the agents are working together. And there's ways to regulate the interaction of the agents. So if AGI was emerging or being created from an interaction of many agents, you could have transparency, you could have auditability, you could have the ability to kind of regulate to some degree some of the safety issues at that interaction level. Okay. Newell and Simon came up with a framework. We heard at some of the other talks. I loved the session on cognitive architectures. John Laird, Paul Rosenblum talking about SOAR. Ben was talking about his. There's 80 different architectures to choose from now. Surely some of these can be adapted to be the glue that can enable human agents and AI agents to work together to have a higher level of cognitive performance. So that's going to be the idea that we need some sort of universal problem-solving architecture or some sort of cognitive architecture that can kind of integrate human and AI agents at the next level. Okay, idea number 4. This comes direct from Herb Simon. So he had, I'm actually going to squeeze 2 ideas in here because I really like a lot of Herb's ideas. So the thing that he's most known for, bounded rationality, won the Nobel Prize in 1978 for this idea, is basically that, intelligent systems, if you're talking about humans, a lot of their behavior can be explained by the fact that we can only remember so many things, we can only process so many things, we have limits on our cognitive abilities. And if you understand those limits, you'll understand human behavior, right? So that's bounded rationality. The flip side of that is what we see with some of these LLMs where you have essentially unbounded memory. So a lot of what their intelligence results from, to the degree that they are behaving intelligently, it's from overcoming those bounds on rationality. You can have such a big memory. That really is a big advantage. Similarly with perception, we're limited to seeing visible light, and I can see only the things that are in front of me in this room. An AI system conceivably could see X-rays and whatever the Hubble Space Telescope is seeing, and could be seeing what sensors all over the planet are seeing. So its perceptual abilities much less bounded than humans. Okay. Collective intelligence, if you have many agents, whether they're humans or AIs, each one knows different things. In combination, they overcome a lot of limits of bounded rationality. And I've seen this in designing other collective intelligence systems with retail investors, which is a completely different domain. But a lot of people said, well, what does a retail investor know? How can they compete with the top hedge funds? Impossible. But turns out each little retail investor knows something different. And if you have millions of them and you can aggregate them, you can actually beat those top hedge funds. And I know this because we did it. So bounded rationality is a key piece here. There's another key idea which is very important for AI safety and which is kind of overlooked a little bit. It's a tiny little book. Herb Simon wrote in 1983 called Reason in Human Affairs, Stanford University Press. And in that book, there's a little quote, "Reason is wholly instrumental. It cannot tell us where to go. At best, it can tell us how to get there." And so this idea goes all the way back to David Hume, the philosopher, 1776, wrote a treatise. I'm not a philosopher, but I sort of trace this back. The idea that you have to get your values from a non-logical source. It's impossible to rationally or logically derive what is right and what is wrong. And when I encountered this idea, it gave me great comfort because there's this notion that somehow superintelligence will become so much smarter than us and it may decide to do us in or something. But why should it? It's not going to reason its way. You could be trillions of times smarter or more logical, able to do more computations than a human being, but still, you cannot reason your way into what is right and what is wrong. You have to get those values somewhere. And where will superintelligence get those values? Well, according to David Hume and Herbert Simon, those values have to come from some non-logical source, and I think the top candidate for that would be humans, especially if humans and AI agents were working together in a system. The humans have maximum chance to expose the AI agents to their values. I'm running low on time, so I'm going to just zoom to the last slide here. So here's putting it all together in a very brief way. Society of Mind says AGI can arise from the collective intelligence of many agents with lesser intelligence. This is what the human brain does. Such systems have been built in various domains that are very narrow. Information theory says we're going to need increasingly rare expertise, and human experts may be a good source of that. Problem-solving theory from Newell and Simon says you need some sort of architecture. Maybe it's SOAR, maybe it's Benz, maybe it's one of the other 80 ones that are out there, but that's the glue to integrate human and AI agents. Bounded rationality says these many agents can be smarter because they overcome limits of bounded rationality. And Herb's thought about there's no rational way to derive values says maybe we don't need to be so worried about AGI destroying us all if we do a good job of exposing AI little by little in context, in the process of problem solving, to the way that humans solve problems ethically. And I could go on a lot more. Let me just say, if there's a lot more information, there's a website, iqcode.com. You could go to superintelligence.com. It'll take you to the same place. And thank you all very much for your attention. I really appreciate it. Thanks.
You can stay here. We'll see if you have questions.
Okay.
Thank you very much, Craig. That was wonderful.
Craig, I'm very much in favor of your collaborative and collective approach, but I want to push back a little bit on the idea that AIs can never work out values by themselves. You must be familiar with the argument that AIs will develop convergent secondary goals in support of whatever primary task has been assigned. Therefore, they won't need to ask humans various things. They'll decide by themselves. But whatever the goal is, they will need to maintain their own existence. They will need to deal with the threats to their own existence, and to the extent they decide that humans might be a threat to their own existence, they might reach that value decision as a calculated heuristic without needing to go back to humans as a source of their values. So how do you assess that convergent values argument?
Yeah, so that's a great point and a strong argument. So I have a bias. And my bias is that the way to get safe AGI or safer AGI is by design, and that the fastest way to get AGI is to design it as a system from the very beginning. So right now we're not at that situation. Luckily, I think there's a limited window. At some point we will be, and under certain design scenarios, everything that you just said I think I'd be very worried about. I have hope that the way in which AGI is designed from the ground up is a system in which AI agents that are customized, so each of us potentially would take Llama 3 or whatever and customize it with our own personality, our own things that we've written, our our value system as well as our expertise, and you'd have many individual AI agents that sort of democratically, in a statistically valid and representative way, reflect the values of everybody in this room and many others. Those would all work together on a network, those AI agents, with humans. And in the beginning stages of this, as a problem comes into the network, if the AI agents know how to solve it, they solve it. If they can't solve it, the humans help them solve it. The AIs learn how the humans do it. And the humans are going to solve those problems, for the most part, in ethical ways. So, quick example, and I don't want to go too long, but if the problem was, I want to go to Paris with my pet, and the AI agent said, let's stick the pet in the overhead bin because it fits. And the human said, no, 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 that's cruelty to animals. I don't believe in that. The AI would learn, okay, in this scenario, you shouldn't do that. So in each individual problem-solving scenario that comes up, because it's interacting with humans, it's learning human ethics and humans' values in a very context-specific way. And also, for every problem that it doesn't know how to solve, the humans are able to have an influence. And further, the AI agents themselves, to begin with, are customized with our values. So all of that gets us off to a good start, where those values are sort of distributed very robustly in a way that's robust to bad actors and robust to, bad things happening in the beginning. Does it remain aligned? I think you have a very good point of whether it would remain aligned sort of in the long-term future. But great question.
Thanks for your great presentation. I have a question. When you're talking about your idea of having this human collective working with these LLMs, it seems that there's a significant technology part that would be missing, because LLMs are essentially like frozen black boxes, right? They're not experiential systems that can have some form of like structured knowledge, on the side or as an aggregate or some hybrid that would work with that human collective as well. So I'm not quite clear on the idea.
So I guess the idea would be LLMs right now, you could ask them to solve a problem. They might not do a very good job of it, but they would try. Or they would give you a response anyway. It might be what you want to hear. It might be hallucinated. In some cases, it might be helpful. They might be able to help you figure out how to get from here to Paris or something. I see the AGI level performance emerging at the network level. So there's kind of a whole bunch of agents, human agents, AI agents, some of which could be customized LLMs. They work together using a shared architecture. That shared architecture is very rigorous and designed to handle any kind of problem-solving activity, which is basically what Newell and Simon, SOAR, a lot of these architectures can do. They're very general. And so somebody comes with a problem and says, I want to do X. They submit it to the network. AI agents take a crack at it. If the AI agents aren't able to do it, human agents guide it. All the problem-solving steps are rigorous. They're all recorded. And next time that problem comes around, maybe you can retrieve the answer, or maybe you're able to solve it a little bit faster. So that's kind of the system that I'm imagining. But to your point of, is there a lot of technical work to create that and make it work? Yeah, absolutely. It took me 14 years just to get a very simple thing to work on Wall Street. This is harder.